In this video, I am going to present on the topic, why classical physics changes at the nanoscale. This topic explains how the laws that successfully describe our everyday world begin to fail when we study matter at extremely small dimensions.
Classical physics works very well for large objects such as planets, machines, or moving vehicles. However, when we move to extremely small sizes, especially at atomic and nanoscale levels, matter behaves very differently. At this scale, quantum effects dominate, and classical laws can no longer fully explain physical behavior. In classical physics, the universe was considered completely predictable. The scientist Pierre-Simon Laplace imagined that if someone knew the position and motion of every particle in the universe, they could predict the entire future. In classical domain, Newton's laws uniquely determine motion. According to Newton's laws, the same starting conditions always produce the same results. This idea suggested that randomness does not truly exist. From a philosophical point of view, free will appears to be an illusion because human decisions may simply result from previous causes.
However, problems appeared even before quantum mechanics developed. Chaos theory showed that very small uncertainties in initial conditions can grow rapidly over time. Systems like weather prediction or fluid motion become impossible to predict accurately. So, the universe remained deterministic in principle, but unpredictable in practice. So although nature remained deterministic in theory, it became unpredictable in practice due to limited knowledge. This unpredictability reflected limits in human knowledge rather than genuine freedom or randomness.
Quantum theory radically changed the picture. A major revolution occurred with quantum mechanics. Physicist Werner Heisenberg demonstrated that uncertainty is not due to measurement errors but is a fundamental property of nature. So the key shift from classical world is, according to quantum, before measurement, particles can exist in multiple possible states simultaneously. After measurement, only one outcome appears. This means reality at microscopic scales becomes probabilistic rather than perfectly determined.
From an important question arises here, does randomness mean freedom? The answer is no. If events are completely determined, there is no freedom. But if events are purely random, there is also no control. Therefore, true free will may require something deeper than both determinism and randomness.
This philosophical conflict is best represented by two giants of physics, Albert Einstein and Niels Bohr. Einstein believed quantum randomness hides deeper deterministic laws and famously argued that nature must have an objective reality independent of observation. Bohr, on the other hand, believed physics describes only what we observe, and probability is fundamental to nature. This debate still influences modern physics today.
Quantum measurement introduces some fascinating questions. Does observation actually affect reality? Is consciousness physically special? Thought experiments proposed by Erwin Schrödinger showed that systems may exist in multiple states until observed. Different interpretations suggest consciousness may collapse quantum states, multiple universes may exist, or hidden variables may determine outcomes. The philosophical interpretation of quantum mechanics will be explained in a separate video.
Now coming to nanoscale physics. The nanoscale ranges from 1 to 100 nanometers. At the nanoscale, particles begin to exhibit wave-like properties, whereas classical physics assumes continuous motion and deterministic behavior. Because of this difference, classical theories fail to accurately describe microscopic phenomena, and quantum mechanics becomes necessary to explain physical behavior. While classical physics works very well for macroscopic objects, it cannot explain atomic and subatomic systems, including the stability of atoms and the existence of discrete energy levels.
At the nanoscale, materials have an extremely large surface-to-volume ratio. This means that a significant number of atoms are located on the surface rather than inside the material. As surface atoms are more reactive, nanoscale materials often show increased chemical activity, changes in melting point, and improved mechanical strength. Therefore, materials at this scale can behave very differently compared to their bulk form. Another important phenomenon at the nanoscale is electron confinement. When electrons are restricted within very small dimensions, their motion becomes limited, leading to what is known as quantum confinement. This confinement changes the electronic and optical properties of materials. For example, quantum dots can emit different colors depending on their size because electron energy levels become discrete.
In conclusion, classical physics breaks down at nanoscale dimensions because quantum effects dominate behavior. Due to surface effects and electron confinement, nanoscale materials behave very differently from bulk materials. These unique properties enable applications in electronics, medicine, sensors, and advanced nanotechnology.